I hope this is the last video. Usually I try to end the lectures with something very beautiful, and this one I don't quite find it so beautiful. Actually, first time I saw this proof I was a bit disappointed that we have to take care of this detail, which is so unpleasant. Anyway, we found BK a family of linearly independent vectors, and since they are linearly independent, we can extend them to get a basis for UK. Okay? How do we extend the basis? Well, we just add more vectors to the family becomes larger, now it has more vectors, and those vectors, they are still linearly independent, and now they span the whole space. And now we use this basis, BK tilde, that we had before, so that's this tilde here, because that's not the same BK we want to get in the end. We add more vectors to it, but now we want to use these vectors together with this basis to construct a Jordan basis. So what we're missing here is the term Jordan. Okay? Why is this not a Jordan basis? Because normally n applied to these vectors does not go to 0. So if you write n with respect to this basis here, it will not be nice. We want to fix that. So this unpleasant property, that's what we want to fix. So how do we do that? Well, pick one of them, call it J, so call it to be Wj, and let's replace it by another vector that now has this property, that now satisfies this. How do we do that? Well, apply n to this vector. When we apply n to this vector, the result is in the range of our operator n restricted to the space where this vector is. Okay? And this vector is in that space. And that range we have already shown before here. This range is just UK plus 1. So when you apply n to this vector, it will be in UK plus 1. What is UK plus 1? That's the span of BK plus 1. And what's the span of BK plus 1? Well, if we take BK tilde is, if we look here in the chain, so we have this is BK plus 1, and BK tilde is when we add these vectors. Okay? So if we apply n to this collection, then this vector comes here. This vector goes to 0. This vector comes here, this vector comes here, this vector goes to 0. Comes here, goes to 0, comes here, goes to 0. So the ones that go to 0, we lose them, but we get exactly the vectors we had before. Okay? So going back there, what's the point here? The point is that UK plus 1 is exactly the span of this vector that we had already, and that's exactly the span of n applied to the vectors in BK tilde. Okay? Which means n Wj equals n xj for some xj. So we can take some xj here, and xj is in there, and we can take xj in there such that xj and wj under n have the same image. So since they have the same image, we can subtract. We can subtract xj from wj, so now we get a vector which is much nicer. Why so much nicer? Because n applied to that vector will be 0. Yeah? This vector is the difference between this one and this one, so when we apply n, we get 0. Okay. And we repeat this process for all of these vectors that we got here. And we observe the following. This collection here will still span UK. Yeah? Why will it still span UK? Well, because all we did was add some vector, subtract some vector from this space, from vectors in W, so from this part here to W, and we know that when we add multiples of one vector in a linearly independent family to another vector, then it doesn't affect this space that they span. Okay, and well, this collection has the right number of vectors. Why the right number? Because these are in correspondence with this, and this was a basis for UK. So if since they span and they have the right number, they are a basis. And this time it's a good basis, it's a Jordan basis. So we replace these bad vectors. They were bad because of this property. We replace them by vectors that have the right property. So now it's a Jordan basis. And this concludes the very long proof of the proposition.